the class. In this episode, we're going to discuss cyclic subgroups, Fermat's little theorem, and something about roots of unity. Okay, so let's recall what a group is. Let's recall what a group is. So a group is a set G that is non-empty, equipped with an operation which we're going to denote for the time being just star, that is binary. So star takes two elements of G and produces also an element of G, such that first of all, star is associated. Second, star admits a neutral element. That is, there's an element E such that when we combine it with any G in the set, we get the same G. And third, each G in G admits an inverse. Respect to star. This means that for each G there's a G tilde such that when we combine it with G, what we get is the neutral element. So notation usually goes like notation. The inverse for G is usually denoted G to the minus 1. Okay, we just call it G inverse. So a group is actually a set G together with this operation which is associated, admits a neutral element, and is closed under taking inverses. Okay, so what do we mean by a subgroup? So if this is a group, what is a subgroup? Okay, so we're gonna give a gentle definition of a subgroup. Let H be a subset of G. We'll say that H is a subgroup of G if, first of all, the neutral element of G belongs to H. Second of all, H is closed under the star operation. So if we have an operation defined on G, then H should be closed under that operation. This means that if H1 and H2 belong to H, then the combination of H1 and H2 should also belong to H. So we summarize that by saying that H is closed under the operation of the group. And thirdly, H is closed under taking inverses. This means that whenever little h belongs to the set H, then the inverse respect to the operation star also belongs to H. Okay, so that's what a subgroup is. Okay, it's not any subset. It's a subset that needs to fulfill certain compatibility conditions with respect to the group operation. Okay, so it's not just any subset. We're going to take a look at a very specific kind of subgroup, and we're going to restrict ourselves to multiplicative notation, but we're just simply simplifying the notation for a star. Okay, this is not anything fancy. Notation for the rest of this video, we're just gonna use the symbol little dot for the group operation. Okay, so we're gonna simply talk about multiplication in general. Okay, so let's do this. Let's take G and G not equal to the identity element. Okay, and let's consider a finite group G. And what about the set of powers of G? Let's call it H, and we're gonna be taking a look at G to the kth power, where K is a natural number. So this is a collection called G that contains G, G squared, G to the third power, G to the fourth power, and so on. Okay, so we're going to prove a theorem about H. H is not any subset. H is a subgroup of G and is in fact a very important subgroup of G. So theorem H is a subgroup of G. Okay, so this is the theorem that we want to prove now. So let's give a proof. Okay, obviously by definition, H is closed under multiplication. And by this we mean that G to the L times G to the M is obviously G to the L plus M. So this is fulfilled, since if L is a natural number, M a natural number, their addition is also a natural number. So H is closed under multiplication. So this is fine, okay? So this is verified. So we're left with two things to check. First of all, that the identity element belongs in H, and also that H is closed under taking inverses. So let's show that H contains the identity element. Let's show that the identity or the neutral element of G belongs to H. Okay, so how do we do that? Okay, we are going to need to to a certain property of the natural numbers and the fact that G is a finite group. So let's do that. Let's see how it goes. So G finite is a finite set. This implies that H is also a finite set. Since H is a subset of G. So H is a finite set. This actually means that the collection G, G squared, G to the third power, and so on, is not infinite. All these powers cannot be all different. G cannot be all different. Okay, so H is a finite set. So this is what's important here. If G is finite, then H is also finite. So what does this tell us? Okay, let's use some properties of the natural numbers to our advantage. Let's call R the set of natural numbers such that G to the M equals to G to the J for some natural number lesser than M. Okay, so this is a set of natural numbers for which G to the M equals one of the powers of G that appeared before. Okay, so for what you have seen, H finite means that R is non-empty. And since R is a non-empty subset, and since R is a non-empty subset of N, the fact of N being well ordered implies that R has a first element. So there's a first natural such that G to that natural number equals G to some other natural number lesser than M. So there exists a minimal M naught such that G to the M naught equals G to the J naught with 1 lesser or equal to J naught less than M naught. Okay, so what we see now is that this means that H has a form G, G squared, third, and so on, G to the J naught, and then and this is it. These are all the different powers that appear in H. The next power of G, that would be G to the M naught, is actually this guy. But we can say more about this. Maybe we can be more specific about the shape of H. So we know that G to the M naught equals to G to the J naught. So since these are elements of G, we can also have the inverse of G to the J naught. So we can multiply both sides and we'll get this. But now the inverse of G to the J naught is G to the minus J naught. And this is simply G to the M naught minus J naught. And since J naught is lesser than M naught, then this subtraction is actually a natural number. So this means that E actually belongs to H, because E is of the form G to some natural number. Okay, so this has proven that H belongs, that E belongs to H. Okay, so there's even more, okay, because this very line tells us more. Okay, so a further look so this line, if we multiply by G, gives us this equality, and this is obviously G to the M naught minus J naught plus 1. So this natural number is that when we raise G to this power, we get G to the power of 1. So this means that M naught minus J naught plus 1 belongs to R. R consisted of the natural numbers which produce repetitions. Okay, so M naught being the smallest element of R gives that M naught should satisfy this inequality. So if we work this out, then we get that J naught is equal or less than 1, and at the same time one was lesser or equal to J naught. Since J naught is a natural number, both of these conditions say that J naught is actually 1. So what does this say about H? H consists of the powers of G. G to the first power, to the squared, cubed, and so on. Then we get all the powers all the way to G to the M naught minus 1. And then what happens is, if we want to take into account J to the M naught, this is J to the first power. So if I place J to the M naught, I'm going to be repeating this one guy. So this is all the set of powers of G. But furthermore, what we have learned is that G to the M naught minus 1 is actually the identity element, because that's what we said before. So this one last guy is actually the identity element. Okay, this shows that H has M naught minus 1 elements, and this is very important. Okay, H has m naught minus 1 elements. All right, so we're only left to prove the third condition for H to be a subgroup. We only have now to prove that H is closed under taking inverses. And that's easy because if I have a power of g, say g to the k, then producing the inverse of g is going to be easy. Because when you actually compute this, g to the k plus m naught minus 1 minus k, this is g to the m naught minus 1, and this is the identity element. And all this works because this is a natural number. So the inverse of g to the k is actually this power of g. Okay, so this says that H is indeed a subgroup of G. Okay, all this was possible by the fact that N was well ordered, okay, and the finiteness of G. So now that we have proven this theorem, there's a lot to say about H and a lot to say about the interaction between the elements of H and G. So first of all, a definition. Let G be a group, G an element of a group, and the order of G is the minimal k belonging to n, such that G to the k equals the identity element. The order is the smallest power of G that equals the neutral element of G. And observation, if H is the collection of the powers of G, then what we have is that the order of H equals the order of the element G. Okay, and definition, subgroups of the shape of H are called cyclic groups. In this case, H is a cyclic subgroup of G. All right, and another observation by Lagrange's theorem. The number of elements in H divides the number of elements of G. Okay, so not only H has a finite number of elements, but the number of elements of H must divide the number of elements of its mother group G. Okay, so this is a very important theorem. is a corollary. If the order of a group is a prime, then G possesses no non-trivial subgroup. That is, when the order of G is prime, it has only two subgroups, the identity element by itself and all of G. It has no intermediate subgroups. All right? So that's an important observation. Okay, so we're gonna try to put this into a more familiar context. Some context. When does this situation arise? For instance, let's pick a natural number greater or equal to 2, and let's define a, the quotient z over n times z. This is what we usually call z sub n. This is the set of residues or equivalence classes of remainders modulo n. So this forms, remember that A is a ring under equivalence class addition or remainder addition. Class of n time plus the class of n equals the class of the sum, and also the class of m times the class of n equals m times n class. Okay, so this is a ring under these two operations. All right, so what we are now gonna be interested in is considering the invariable elements for multiplication. Let's now consider the units of A. This is the classes such that M has an inverse respective multiplication. Okay, so this subset together with multiplication is a group. We'll call it G. Okay, so the units with class multiplication is actually a group, and we can do stuff with this G as we did in the previous section of the class. Now, clearly, the number of elements of G, that is the amount of units, is actually phi to the n, with phi the Euler function. You can take this as the definition of the Euler function, if you will. Okay, so we know that for any class belonging to the units of A, then we know that the order of H must divide the order of G. That is, this divides phi of n. Okay, the multiplicative order of an invertible class must divide phi of n. Okay, so let's do some computations with some fixed numbers so we get a hold of this. For instance, let's take n equal to 4. So this is the collection of these classes, and we are going to need the units of C4, the invariable elements. So 1 is an invariable element, 2 is not an invariable element because 2 times 2 is 0, so that means that the class of 2 is a divisor of 0, so that cannot be an invariable element. So same with 3 because, well, 3 times 3, that's 9. And that's congruent to 1, modulo 4. So 3, the class of 3 has the class of 3 as its own inverse. Okay, so here what we have is that phi of 4 is the number of elements in this set, and that is 2. Okay, and if you take a look, then the units of C4 have a prime number of elements. So this group has no non-trivial subgroups. As a matter of fact, this can be considered as 3 and class of 3 squared. We say that this group G is cyclic and is generated by 3. Because all the elements of G are actually powers of the class of 3. This guy being exactly this guy. So we have shown with an example that cyclic groups, that we have plenty of cyclic groups. We have used a very small example with n equals to 4. So there are cases in which there are more. Okay, let's do one more. Let's take say n equal to 6. Okay, so sets of 6. This is the collection of classes. Okay, and we are gonna need the units of this ring. So we need to discard all the 0 divisors. So these two guys are discarded. Then this is also discarded because the class of 3 times the class of 4, that's the class of 12, and that's the class of 6, that's 0. Okay, so all these guys are discarded as well as the class of 6. So the units of set 6 are actually the class of 1 and the class of 5. And this again is the group generated by the class of 5. Okay, so observation, the class of K is invariable if and only if K is coprime to N. Is to have no common factors with N. Right? Now we will see that the order of an element and the interaction with the order of the group in this context that we're talking about this ring, gives actually a very well-known and important result in elementary number theory, which is called the Fermat's little theorem. Okay, so let's go back to the bigger context and let G be a finite group, G an element of G that is not the identity element. Then theorem, G to the order of the group equals the identity element. Okay, so what does this mean? Okay, let's do a proof of this. Let H be the subgroup generated by G, and then by Lagrange's theorem, we know that the order of H divides the order of G. That is, there's an integer k such that the number of elements of G equals k times the number of elements of H. So this means that this is k times the order of G, because by definition the number of elements of H is actually the order of G. So this means that G raised to the number of elements of G, that's G to the k times the order of G, and this is just G to the order of G all to the kth power, and by definition this is the identity to the kth power, and this is simply the identity element. Okay, so this is a very important result, and in the context that we were just discussing, gives a very powerful tool to start studying number theory. Okay, so as a corollary, so in the context of G being the units of z to the n, this says that G to the order of G, which is phi of n, is actually the identity element. It is congruent to 1 modulo n. This is the Euler-Fermat theorem. Okay, then another corollary is, let P be a prime. So first of all, phi P is actually P minus 1, since every integer greater than 0 and lesser than P is actually co-prime with P, because P has no non-trivial factors. Then what we have here is that G to the P minus 1 is actually congruent to 1 modulo P, and this is what it's called Fermat's little theorem. Okay, so this is a very important result, and this also gives corollary in Z sub P. There's an equality. We have the equality G to the P minus 1 equals 1 modulo P, which is also sustained modulo P. And this is valid for all G in set P. Whereas this one, G, needs to be different from the identity. It needs not to be 1. If we work this one out, this says that g to the p minus g equals 0 in the set of classes. So every element of this field is a root of a polynomial p of t. Let's use a different letter, f of t, t to the p minus t. Okay, so we have characterized a finite field as the set of roots of a certain polynomial. Okay, so the theory of groups is very rich. Okay, and even in these very simple cases, and in a general scenario, if we go a little bit more deep, then what we have is this wonderful set of results stemming from number theory, and then we're going to be taking a look at different approaches to field theory. So let's study more groups. So let's start with an example. Let's take a look at the polynomial p of x, x to the 4th power minus 1, and we're going to be taking a look at p of x as a polynomial with real coefficients. Okay, so what do we know about the roots of p? We know about the roots of p. Okay, we know that there's at least one real root. That is, p of 1 is actually 0. And we also know that p of minus 1 is also 0. Right? So p has two real roots. P has at least two real roots. And as a matter of fact, p of x can be factored as this. All right? So this is a factorization of p of x over r of x. It's a factorization which uses all polynomials with real coefficients. And since this has no real roots and is of degree 2, then this factor lying right here is an irreducible factor. Irreducible factor over r of x. So p has exactly two roots in r, and its factorization includes a polynomial of degree 2 which is irreducible over r of x. So what if we wanted all of the roots of p? Then we know that there's a field that we can construct which actually has at least one more root of p. We know how to construct a field F containing a non-real root of p. Let's remember how to do that. Okay, let's call q of x this irreducible factor that appears in the factorization of P. And let's take f to be the quotient of R of x by this polynomial. Okay, so since Q is irreducible, then F is a field containing R, of course, and also in which X is a root of Q of t squared plus 1 when viewed as a polynomial with coefficients in f. Okay, with coefficients in f. Okay, so Q evaluated at x is x squared minus 1, and this is 0 in this new field f. Remember, for R, big X is a formal symbol. It's not an element of the field. But in F, now X is an element of the field. Okay? So this is crucial. In R, X is not an element of the field. But in F, X is an element of the field. And this is very important thing to notice. So we are able to construct a field F that now contains a root of Q. But so Q has X as a root. So we can divide. This means that we can divide Q by the polynomial t minus x. So let's gather a Q, which Q of t was t squared plus 1, and we're gonna divide by t minus x. So how do we do that? By our very good old friend Ruffini's rule. So we lower the first coefficient, we multiply, and then we add. And remember that x squared plus 1 is actually 0 in f. So this means that these are the coefficients of Q, and these are the coefficients of the quotient. This means that Q of t can be factored as t plus x times t minus x. So one of the things that we notice is that x belongs to f, minus x also belongs to f. So these are two polynomials that belong to f of t, those polynomials with coefficients in f. All right, and not only that, but also since x squared plus 1 is 0, right? In f, we get that x squared is equal to minus 1. So if we multiply both sides by x, x cubed is minus x. So what do we see here? That x cubed is actually the other root. X cubed is the other root of q of t. Not only x is a root of q, but x cubed is the other root of q. So this is a very important fact. When adding a root of q to our base field, to R, we also added the other. So if you want to be taking a look at this, adding x gives actually f. Okay, so this means that when q is an irreducible polynomial and we add to the base field one of the roots, we are also adding the other roots. So we say gives all the roots of q, and all these roots are conjugate to one another when q is irreducible. All these roots are called conjugate. Okay, so in this new field f, x is an element of the field, and x cubed gives minus x, x squared gives minus 1, and if you take a look at x to the fourth, then what you have is x squared minus 1, and this is minus 1, and this is 1. So this is interesting. 1, x, x squared, and x fourth are all the roots of p, because x squared was a root of p, x to the fourth power is a root of p, and then x and x cubed were the roots of q. So this collection consists of all the roots of p. Traditionally, R of x, when we take the quotient for considering q, this is called c, and the symbol x will stand with the letter I. This new element has this property that when you square it, you get minus 1. So you can visualize f, the field that we were talking about, as the complex numbers, okay? And there's a graphic disposition of the roots. Okay, so take a, for instance, I'll look at the unit circle. All the roots are 1, minus 1, I, and minus I. Okay, so this is the group of fourth roots of unity. All of these elements satisfy the equation t to the 4 minus 1 equals 0, or t to the 4th power equals 1. All of these elements satisfy this equation, and we view them as elements of C. Another thing that we have seen is that simply with x we were able to describe all of them. So this is what we call a primitive root of unity. I is a primitive root of unity of order 4. It's able to generate the fourth roots of unity. 1i minus 1 minus I is actually this group. Cyclic group, because it's generated by I. All right? So there's an interaction between what we know from groups and what we have learned in the context of fields. What I have done here with p of x as a polynomial with real coefficients can be done when the base field is a finite field. And that is very much important, because in this context, complex numbers are going to give us a lead in how to represent polynomials, not by their coefficients, but by their values. If a polynomial has degree n, then n plus 1 points, evaluating the polynomial in n plus 1 points, will represent the polynomial as a list of numbers, as a list of n plus 1 numbers. Well, the question is how to choose those points to evaluate the polynomial. Well, one way of doing it is using complex numbers. And not only using complex numbers, but using roots of unity. When we use roots of unity to evaluate polynomials, we enter the dimension of the fast Fourier transform. And when we are talking about roots of unity of order a power of 2, then the process of codifying a polynomial as a list of numbers will avoid us, will save us from doing too much work. Usually the way of codifying a polynomial as a list of results takes n squared operations if the polynomial is of degree n. When we use roots of unity of power of 2, then it becomes a recursive problem, and the complexity is n times log n, so that is much lower. Okay, so I wanted to talk about this now because in the following videos we're gonna delve deeper into roots of unity viewed as subsets of the complex numbers, and after we do that, we're gonna discuss fast Fourier transform and its inverse, and then we're gonna see what do we need to do that with a finite field. Okay, once we get to know that, then we'll be able to talk about low degree testing, which is a very important thing in cryptography. Okay, so this is it for now. Hope you enjoyed the video, and we'll be back soon. Okay, see you in the next one.